The scientific method is really one of the greatest tools that humankind has. And let me just try this here. Okay. I've just simplified all the steps. You know, if you look up the scientific method on Wikipedia, there's like a 10-step process. I just simplified all this. You start off with a question. Then you come up with your hypothesis, which is kind of your best guess of what the answer is. You test it with an experiment. You test your hypothesis. You got to do some math or some looking at data and see if you see any patterns. That's called analysis. And finally, you're going to just say, here's my answer. Here's what I think it is. That's your conclusion. So the first part of it is the question. This is really the only reason for using the scientific method. If you don't have a question, there's no reason to use it. A question is just a problem you have or an unsolved mystery. So we've got a problem. Climate change is a severe problem. How can we solve this? That is our unsolved mystery. Now, it's always preceded and followed by observations. To figure out what your question is, you can't just come up with a question out of thin air. You need some observations. I've been observing carbon dioxide levels rising in the atmosphere ever since I started teaching back in the early 90s. Carbon dioxide levels continued rising and rising and rising, and our climate keeps getting hotter and hotter and hotter on average. So that's our problem, and it was obviously preceded by some observations. The other thing is that there are some questions that cannot be answered by science, you guys. Science doesn't have all the answers because they're matters of the heart that may not be answerable by science. I guess in some ways you could, like you could, go out on a date with one person, say, oh, I didn't have that much fun, then go out on a date with another person and have a lot of fun. That's an experiment, but there are some questions that can't be answered. For example, I've been doing a lot of philosophical studies lately and a lot of meditation. Turns out, at least according to many spiritual teachers and my own experience, a lot of people really think that they are their thinking mind. Yes, people think, oh, I am a teacher. I am filling this role. Yes, none of that's real. You are so much more than that. The thinking mind is just part of your experience. It's not the whole thing. Don't think that you are just someone who thinks. There's a lot more to you than the thinking mind. Now, if people are interested in philosophy, I'd be happy to talk about that with you later. Anyway, bottom line, can't answer everything with science. Okay, scientific hypothesis. This is what you believe to be the answer. That's kind of like your guess or your best guess. The thing about a scientific hypothesis is it's gotta be testable. You have to be able to test it with an experiment or it's not a scientific hypothesis. Let's try this example here. Which, if either one of these, Josh, you had a question?
Yeah, you said it has to be testable, but whoever hypothesized dark matter, like dark matter can't be interacted with, so it's pretty much impossible to test for its existence.
Great question. Turns out dark matter can interact. It just doesn't interact with light. It interacts gravitationally. So we have actually seen dark matter because we had these two galaxies collide, and we saw that due to the bending of light from gravity, that there was a bunch of dark matter that collided in that collision. So it can be observed, but not with electromagnetic waves like light. It gives off no light. That's why it's called dark matter. Great question. You must be able to observe it.
Unless it's already other dark matter, I'm guessing.
What's that?
And you can't exactly touch dark matter.
Well, we may be touching dark matter right now. It may be actually going through our bodies. We don't know. We're still in the early stages. Dark matter was only discovered in approximately 1998. So there's still a lot of questions. There are a lot of questions. Let's try this to see if you guys get the idea of a scientific hypothesis. I've got two choices here. Which ones of these is scientific? The Earth is flat is number one. The Earth is surrounded by a completely undetectable force field is two. Which of those is a scientific hypothesis? And I'll just wait till everyone answers. I may have to call on you if you are not answering. So it looks like most people actually have it right that the correct answer is the Earth is flat. And you might be saying, what? How is that a scientific hypothesis? Turns out that is testable. All you got to do is use a satellite and go to the International Space Station and just observe the shape of the Earth. Satellites can't orbit around flat things. It won't work. So if the Earth was flat, none of our communication satellites would work. So there's some stupid people out there, that's for sure. They'll tell you anything. And if you believe them, that makes you kind of mix with them well. Anyway, turns out that this is not testable. The Earth is surrounded by a completely undetectable force field. You can't test that. So it's not a scientific hypothesis. There's no way to prove or disprove that. The experiment is probably the most important thing we're going to spend the most time on today. It's designed specifically to answer the question, to test the hypothesis. So here's some things about your experiment. You got to use as many trials as possible. Use as many trials as possible. Number two, you only change one variable. You can't change more than one thing in an experiment. You change one thing, and then you see if changing that thing causes a change in something else. We call it the independent variable. That's the one that you change. One way to remember this, there's a little mnemonic. I change the independent variable, because you're the one that changes it. So you could say, hey, I change it. And then that's how you remember that. It's the one that you change, that you have a choice about. Leave everything else unchanged. If you change more than one thing, it's going to be a bad experiment. And then what will happen is you change the independent variable. I change the independent variable, depending on your perspective. But then nature will respond, or it might not, with a change in the dependent variable. We have no control over the dependent variable. Nature has control of that. So I change the independent, I for independent, but nature's got the dependent taken care of. Okay, let's try this. An experimenter wishes to determine which format of instruction, lecture or lab, leads to greater improvement in test scores. So here's their design. I want you guys to figure out what's going on here. What's the design? What's the independent variable? What's the dependent variable? And if there's any improvements we could make here. So they're trying to figure out which is better, lecture or lab. That's the question. Which format of instruction leads to greater improvements in physics scores? Let's see. So here's what they do. A class, and you guys, this is where you got to pay attention, because this is where some of the hints come in. So a class of freshmen is given a pre-test, a lecture, then a post-test. So we got these freshmen, you give them a pre-test on physics, you lecture at them, and then you give them a post-test, okay? Then a different class, it turns out it's a class of juniors. They're given a pre-test, they're given a lab, and then they're given that same post-test. What is the intended independent variable? Write that down on your piece of paper. So what is the intended independent variable? And if you use the mnemonic, that will help. What is the intended independent variable? Okay, so Natalia, what do you think that intended independent variable might be?
The format of instruction.
You have got it exactly right. What I change is the format of instruction, okay? Now, that is lecture versus lab. That's what so I could change, or I'm going to give this group a lecture, I'm going to give this group a lab. That's the intended independent variable. That's what they're trying to find out, how that affects something else. The dependent variable, though, would be what? And Emmanuel, what you got your camera off, so I'm calling on those folks more. What do you say would be the dependent variable? Emmanuel, are you there? Hey.
It says scores.
Well, kind of. It definitely is related to test scores, but notice that some kids might be smarter to begin with, so we're looking at slightly different, the change in test score. Does that make sense? Because some kids may start off smarter. So we want to figure out if we affected them with a change in test scores, okay? So that is what nature might give some kids a higher test score. That's what we want to find out, or a bigger change would be it. So here's the thing. There is something very wrong with this experimental design. There's something horribly wrong with it. Okay, I just want you to think about this for a second, and then I'll give you a chance to answer here. Okay,
I-
Josh, do you think you know what it is?
Yeah. In one class, he uses freshmen. In the other, he uses juniors. He is changing two
Correct.
variables at once.
You're changing more than one variable. This group was a freshman and they got a lecture. This group was juniors and they got a lab. That's changing two things. If the juniors do better, if they gain more points, maybe it's because they're juniors. We don't know. We changed too many things. How could I fix this so that wouldn't happen? Can anybody help me here with how that would be fixed? Blake, what do you think would be a better way to do this?
Using students that are the same grade level.
Yeah, just make them the same grade level. That's all you'd have to do, and then do the same experiment. Great. Cool. So we just want to change one thing. Two variables that are changed are age and lecture. We don't want to do that. We want to have them, to improve it, just have both classes be the same age. There you go. Great. Now, when you do this experiment, there's a couple things that we're going to be doing. You collect and record data. You're going to show all your trials. Never just write down averages. Averages can be very misleading, as I'll show you on the next slide. You should write down all your trials. You cross off outliers. Does anybody know what an outlier is? Anybody know what an outlier is? What do you say, Sydney? What do you think an outlier is?
It's like something that's like way different than the rest of the data.
Yeah, you may have to talk a little bit louder, but you're right. It's something that doesn't fit in with the data. It seems very different, like something's just wrong. So outliers are things that don't seem to fit. So if you find those, and you do very often, don't erase them. Don't say, oh, that's wrong, I got to erase that. You just cross them off. It turns out that outliers, actually what you think is an outlier, may be the right result, and that your other ones are wrong. So don't erase anything. Just cross them off if you think they're outliers. You can show averages excluding outliers as appropriate. So here's what that would look like. Let's say, whoops, let me go back a bit. So here is a situation right here. I've got this data here. So this is a time for, let's say, some kind of a, okay. This is the time for some kind of a race or something. I had a snail that was going some kind of a distance, and I timed how long it took. And it was, this is data for the same thing that happened. Does anybody notice something weird here? Anybody notice anything weird with this data?
It's like,
say again?
There's no like specific order that the time is going in.
Okay, well, if the thing is I'm measuring the same thing over and over again, so the order, I can see you saying that. There doesn't seem to be like a necessary things getting bigger and bigger and smaller and smaller and smaller. So that might be something you'd notice. But because I'm measuring the same event many, many times, for example, I have a snail, I race it for how long it takes to go 2 millimeters. And these are the times every time. So can anybody else come up with something else that if you got to really look at the data to see what's going on, it's trying to measure the same thing over and over again. Aris, what do you say here?
Wouldn't it be how the 350 is included and isn't crossed out?
Aha! There seems to be an outlier right there. Problem is, the person just didn't notice that and they just averaged all these to get 2 seconds. Here's the better way to do that. Here's the correct way. See this? You just cross off that one that doesn't seem to fit. That's an outlier. This is 1.5, 1.48, 1.52. These are all about the same. That one doesn't seem to fit. Doesn't this average make a lot more sense? It's about 1.5 seconds if you eliminate that outlier. So always get rid of outliers by drawing a line through them. Don't erase them, and you don't include those in your averages. Any questions about that part right there? Any questions about that? Okay.
Is there ever a part
Yes,
where you
question.
go back to see what caused the outliers?
Well, you can do that. That's an important thing. But if it's just one, a lot of times we won't even know which ones are the outliers till we look at, like, for example, a graph. Then we'll say, oh, now I see that. You do want to figure that out because if everyone's an outlier, then something's wrong with your experiment. So good point. Okay, next up is this, the analysis. This is where we do most of the work. We do calculations, graphs, visualize the data with graphs, find mathematical relationships. Is there a line or a parabola that somehow this data fits onto? You want to compare your trials. There's a couple different ways. We're going to consider uncertainty. That's another lesson. But we can find differences using percent difference, and we can find differences using percent error. These are different things. Percent difference, and I will give you the equations for these, is when you've got two experimental values you're comparing. Percent error is when you have a theoretical and an experimental value. We'll learn how to do both of those calculations. Finally, you get your conclusion, which is where you actually try to interpret the meaning of what happened. And you must state very specifically what was shown by your data and analysis. And if there was experimental error, like Josh mentioned, you want to figure out what was going on with that outlier, this is where you mention what was going on, what happened, how did you get an outlier. Okay, cool. So you guys got a couple of checks for understanding here for you. Which of these is a scientific hypothesis? I've got three choices for you. JB is over 4 meters tall. That's one. Number two, physics is more important than chemistry. Number three, computing power will continue to grow exponentially into the future. Which one is a scientific hypothesis? Okay, great. We've got a lot of people answering, and most people have answered right. Let's go ahead and check this out. You guys, only one of these could be possibly a scientific hypothesis. And it doesn't matter how smart or scientific-y it sounds. The correct answer is number one, as most of you guys guessed. That is the only one that is testable. You cannot test the other ones. Why is it that I cannot test number two? Physics is more important than chemistry. Maybe I feel that's right, but that's an opinion. If you ask Miss Ismail, she'll say, oh no, chemistry is more important than physics. But that's somebody's opinion. You can't really say one is wrong and one is right. This third one, this can't be tested. Computing power will continue to grow exponentially. Now, it is growing exponentially. It doubles every 18 months, but I can't guarantee that into the future. You could rewrite that to say, you know, for the next couple of years, but that would be a different hypothesis. All right, cool. Next up, a couple more checks for understanding here. Now, here's where I'm going to ask you to turn your camera on. Limited to using only the fingers on your two hands, I want you to show me how many trials would produce the most definitive experimental results. Now, this is a little bit of a puzzle. There is a best answer that most people don't do. And notice, here's my hint. I didn't say necessarily hold up the number of fingers. I said limited to using the fingers on your hands. What's the best number of trials in an experiment? So there is a trick answer here that will actually be more correct. Yeah, you guys, the best number would be infinity. A lot of people had 10. You want to have the most trials possible. If you want a scientific experiment to actually give you a definitive answer, like this is guaranteed the answer, you can't get that from science. What we do is we keep doing trial for trial for trial, and we keep saying, oh, this seems to keep working. If you could do infinity trials, that is the only way you could actually prove something. Now, we can't do infinity trials, but we can do as many as possible. So anyway, you want to do the most trials possible. That's really the only way. You guys, I've had people say, oh, 3 trials is the best. You guys, 3 trials is only better than the worst 2. What's the worst number of trials to do? Hold up that number. Even worse than 1 is 0. If you don't do any trials, you haven't done an experiment. If you do an experiment, the worst number of trials is 1. You know nothing. You guys, it'd be like saying you flip a coin. Oh, it turns out heads. I guess it always turns out heads. Totally false. You know nothing from 1 trial. 3 is also bad. 2 is like worse than 3, but 3 is bad. 10, you're starting to get to a number that might be reasonable.